This is an exam review for Process Dynamics and Control for Section 1 of the course on modeling. First question here is how to design a control system with an actuator, sensor, and controller. Lists at least 3 examples of control systems. In this case, these are feedback control systems, and detail the 3 elements of each. So let's think about, first of all, an automobile, cruise control. And our sensor is going to be the speedometer. Our actuator is going to be the gas pedal or a fuel valve. And then the objective, control objective or set point is a speed set point. Okay, our control system 2 might be a thermostat in your home. And in this home, your sensor, you're going to have a thermistor or a thermometer of some sort. Okay, your actuator is going to be your heater, and then your controller objective or set point is going to be your thermostat. You're going to have a set point, so you're going to have a temperature set point in your home. Next, control system 3. I'm just going to show you an example of this with SimTune. It's a nice program that helps with teaching control system and identification. Let's just go to one of the training modules, flow controller, and there you can see it on the right. I'm going to make this just a little bit bigger so you can see it as I begin the simulation. I'll just change it to manual and begin the simulation. We have control over the valve, so that's going to be our actuator, is the valve, and we can move that valve open or shut. Okay, so here it's completely closed right now. And then if I switch it to something like 50%, then it's going to level out. Okay, and if I switch it to something that's more than 50%, about 80% open, then it's going to start to drain. So you can see the blue line there, solid darker blue line, that's going to start to go down. So we have a set point. We might try to get it all the way to, for example, to that green line there, and then we'd have a controller that would automatically adjust that. So we have a set point, let's say, and that's going to adjust the valve going down, and there you can see it's going to try to start controlling this. We have a set point, a PV, the process variable, and an OP, which is our output. Okay, so OP, another name for that is our manipulated variable, the one that we can change or the controller can change. The PV is also called the controlled variable. That one is going to be the one that we can, we're trying to adjust to a certain set point. For example, we had a little bit of overshoot here as it went up, but it'll eventually level into the new control set point there. Now this is an example of a PID controller that's not very well tuned. We're going to learn a little bit more about how to tune these controllers so that we get a certain amount of overshoot or response that we see with the controller performance. Okay, so here's another example of a controller. Okay, so in that control system 3, sensor is going to be the level. The actuator is the valve, and often it's a valve or a pump or a compressor or something that's our actuator that's able to make that change. And then we have a level set point. So when you have the sensor and the set point, are the sensors measuring the thing that we're trying to drive to the set point, that's called feedback control. Okay, and feed forward control is when those two aren't the same. You're measuring something else and trying to predict its effect on the desired outcome. And so that would be feed forward control. Okay, let's go on to the next one. Process has the following step response with 1 input and 2 outputs. We want to try to come up with a first order plus dead time model for each of these. We got 3 parameters on those. You have KP, tau p, and theta p for each of those. So let's just consider this first one right here. Okay, this is when I start, and the first thing I want to do is come up with my delta y, and that's going to be about 0.05 moles per liter. And my delta U is how much I change in my input, and that's going to be about -5 Kelvin. So the first thing I want to do is come up with my gain. And my gain is going to be, for this first one, that's just going to be my delta Y1 over delta U. And so it's 0.05 moles per liter divided by -5 Kelvin, or about -0.01 moles per liter per Kelvin. The next thing I want to do is come up with my dead time. So the way I can do that is go ahead and just look at the inflection point of this, draw the tangent to it, and draw a line over where it started, and where those two meet up, that's approximately my dead time. So this is going to be my theta p, and my theta p is about 0.1 minutes. Okay, after the dead time, I want to see how long it takes to get 63% of the way there. So this is about 63% of the way there. You'd multiply the 0.05 times 0.63 and then come up with the certain level right there, where it crosses, and you draw your time, you identify the time at which that takes place, and then you look at this region of time right here. Okay, after the dead time stops and you start moving up, that's going to be the amount, the time constant. So my time constant is going to be about 1.1 minutes. So there I have a process model, Kp, theta p, and tau p for this, for the concentration. Let's do it for the next one as well, the temperature. Okay, the temperature response, so I consider the cooling jacket temperature and the temperature between the input and the output 2. So this was for number 1 right here. And if I do the same thing for this one, the Kp is going to be about -7 Kelvin divided by -5 Kelvin. So that's 7/5, and those two units are going to cancel. Okay, and then my dead time, it looks like I really don't have any dead time there, so I'm just going to say that's 0 minutes. And then my time constant, here's about 63% of the way there. And so it's about that amount of time, which looks to be about 0.6 minutes. It's just an estimate, you don't have to be very exact. But there is my process model number 2, between the temperature of the reactor and the cooling jacket. Okay, so that's an example of how to empirically fit these models. Let's come on down to the next one. Now this is a different approach for obtaining a model. This would be from a first principles approach. Okay, so we have on the diagram indicate which quantities are manipulated variables, controlled variables, and potential disturbance variables. Okay, this one we're trying to maintain a certain temperature of a reactor. So that is going to be the controlled variable. The cooling jacket temperature, that's going to be our manipulated variable, a thing that we can adjust. That's also going to be called the controller output, or just the output. And this one is sometimes referred to as a PV, and that one sometimes as an OP. Okay, and then we'd also have a set point associated with this one as well. A couple of disturbance variables. You might have some feed conditions, and you might have something like the ambient temperature. That could be another disturbance variable. So there's a couple of different disturbance variables that you could think of. Okay, I'm just going to do this problem just for the, well, I'll set it up for both of them, but I'll run through the rest of them just for the concentration. You can do the energy balance yourself. Okay, so we're going to write the transient species balance, calculate Ca. And so what I'm going to do first of all is just do dN Na, the number of moles with respect to time, and that is going to be the number of moles in, number of moles out, plus the reaction rate of A times V. Now the reaction rate of A, let's just say that equals, it wasn't given to us, so let's go ahead and say that's negative K times Ca. It's just a first order reaction. K is not dependent on temperature. If it were, it would make it just a little bit more complicated, but you could do that one as well. Okay, so this one is going to get plugged in right here. Here's our species balance. So we've written it out. We want to get it in terms of concentration, and so we know that Na equals the concentration of A times the volume, and we know that Na dot, the rate, is going to be equal to concentration of A times the volumetric flow. So you can substitute those in, and if you assume that it's constant volume, then that's going to come out front. And then I have the concentration of A in the feed minus the concentration of A leaving times Q plus the, let's see, I'm going to have negative K Ca times the volume. I just substitute in reaction rate of A. Okay, so now I have it in terms of Ca, and if I just divide by V, then I have the, on the left hand side is just dCA dt, and there I have my differential equation. Okay, for an energy balance, it's going to be similar. If I assume closed system and compressible fluid, then I can write in terms of the enthalpy. Okay, and then I also have a cooling jacket. And then I also have the heat of reaction. Just make sure, because it's exothermic, that whatever the signs work out to be, this term should be positive as you react A. Okay, I know that my enthalpy is going to be equal to my mass times the heat capacity, temperature minus temperature reference. Choose all those to be the same, then it's going to be working out to be m c sub p. You can replace that with rho v if you wanted to, and then we have dt equals, okay, and then I have my let's see, I have my rho, my volumetric flow rate times c sub p, temperature feed minus temperature leaving, plus UA TC minus T, okay, plus heat of reaction times minus K Ca times V. Okay, so here's my energy balance. I could divide all of that by rho V C sub P and just isolate the derivative on the left hand side. Okay, there's my energy balance and my species balance. Let's go ahead and calculate the steady state values of each. So to calculate steady state values, you just assume that the derivative equals 0. So let's do that for the first one. We have what's on this side is going to be Q CAF minus CA minus K CAV divided by V. V is just going to cancel out. Okay, I'm going to collect all the CA terms on one side and put my CAF onto the other side. And so that's going to be Ca times negative Q minus KV. Okay, so Ca, and this is going to be my steady state value, is going to be equal to Q Ca feed divided by Q plus KV. If I give you a numeric answer, that could work out to be just a number in the end. Okay, I have my steady state value for CA. Now let's do it for the temperature as well. So in this case, I just set the derivative equal to 0. This denominator term is just going to go away. And let's solve for temperature. Okay, so I'm going to move everything that's not temperature onto the other side. There's a feed. And then I'm also going to have UA times TC on the other side. And then I'm going to have, that's going to turn into a positive. And I can plug in the steady state value there for CA. And then on the right hand side, I'm going to have the rest of the terms that involve T. Okay, let me move this over just a little bit. Okay, so I think I've worked all that out. And then I'm just going to solve for, factor out T on the one side. And so T steady state is going to be, I'll just write this a little bit different, so I'm going to write it all out. And that's going to be negative rho Q C sub P plus minus UA. Okay, and that's going to be equal to temperature steady state. Okay, and so that's going to be a number in the end. If you plugged in all the values, that would be a number. Okay, so we've gotten our concentration of A steady state and also our temperature steady state. And that's important because we want to have those for linearization. When we linearize these equations, we want to get it into this form, and so we want to choose points that are at steady state conditions, and we'll define some deviation variables. We'll call those the prime values. Those are going to be our concentration minus that concentration of A steady state and temperature steady state. And so we're going to linearize. We're going to take our function here up above. Okay, we're going to start with that one again, and then we're just going to linearize this. The way you linearize anything, if it's a function of f of x comma y, that's just going to be equal to the nominal values plus the partial with respect to x. Okay, you plug in x and y nominal values, and x minus x nominal plus the partial with respect to y, and plug in the nominal values again, y minus y naught. We rename this as like y prime, and we rename that one as x prime. Okay, to get it back into our steady state form. And I'll just rename that as y prime. Okay, if we choose steady state values, then this first term is going to go away because that's going to be equal to our derivative at the nominal values, and we know the derivative is equal to 0 at steady state conditions. So we're just left with the remaining terms right there, and those are all of these right here. Okay, so we just have to take the partials of those with respect to each of the variables, and that becomes our alpha 1, alpha 2, and so on. So let's just do that. We have the first one is CA, the second one is temperature, the third one is TC. Okay, I just want to take the partial of this with respect to CA, and that's going to be equal to negative Q divided by V. Okay, and then we're also going to have minus let's see, K. So I just took the partial with respect to CA, and that is going to be equal to alpha 1. So let me just write that down here. I'll make this just a little bit smaller. That's going to be negative Q over V minus K. Now you'll notice as well in that equation that there are no temperatures. So the partial with respect to temperature and partial with respect to temperature of the cooling jacket is going to be equal to 0. So those are not there at all. Let's go ahead and do this as well for our energy balance. Okay, so I just need to take the partial of this right hand side of the expression. Okay, that's our F with respect to CA, and that's going to be equal to negative heat of reaction, okay, times K times V divided by rho V C sub P, and that's going to be equal to beta 1. I'm going to take the partial with respect to temperature, and that is going to be negative rho Q C sub P minus UA divided by rho V C sub P. So that right there is going to be equal to beta 2. And then let's take our partial derivative with respect to TC, and that is just going to be UA divided by rho V C sub P, and that's going to be equal to beta 3. Okay, now those are all just going to become numbers if I had given you values, but go ahead and plug those in just in symbolic form down here into the boxes for the answer. Okay, so that's how you develop a linear model. You start with the nonlinear equations and you can linearize it. And so it's different than our step response models, which are empirical. We're deriving those from first principles. Let's get back to our empirical models again. Let's write a problem that demonstrates the knowledge of how to use a first order linear system with time delay, as shown below. So here are the equations, and we've gone over those a bit in class. If you need a review on those, I'd recommend coming back to the course, and we're reviewing for this dynamic modeling exam, and here are all of the topics. And if you need a review on the first order systems, I just say come to this page, and there's a lot of information and just about how to get process gains, time constants, and delays. So I really want you to know this equation. Again, we fit models with graphical or optimization method, but I also want you to know this equation and how it is and how it's used. Okay, so let's just think of a problem. This is kind of a different question here. It's very open-ended, but let's say you went to an auto dealer and you wanted to try to get a first order plus dead time model for an automobile. And you're going to ask the auto salesman a couple questions about the car and its performance. Okay, so let's say you asked, he gave you some information that the max velocity is 150 miles per hour, that the 0 to 60 miles per hour is 10 seconds. And then you also asked him some information about, well, when you punch the gas pedal, how long does it take to respond? And so he says that there's a 1 second delay just as the turbocharger is ramping up before the car starts lurching forward. So 1 second delay there. So we want to use this information right here to come up with our Kp, our tau p, and our theta p for our first order model. So max speed probably means that you have the accelerator pressed down to 100%, and then you're going to go up to 150 miles per hour. Okay, starting from 0. Okay, there's about a 1 second delay in that, so that's going to be equal to our theta p. Theta p is going to be 1 second. That's our dead time. Our gain then is going to be our total delta y output divided by our delta u input, which is our gas pedal. So that's going to be 150 miles per hour for 100% on your pedal. So that's going to be 1.5 miles per hour per percent pedal. And the last thing that we need is our time constant. So it gets up to 60 miles an hour at in 9 more seconds. So the dead time, you'd include that, but then you also have an additional 9 seconds to get up to 60 miles per hour. So what is our time constant there? We're going to use this formula that we had where x of t equals, for a step response, 1 minus e to the minus, and this is t minus theta p over tau p. Okay, and then we also have kp delta u. So we're at 60 miles an hour. We have 1 minus, and then t minus theta p. This is going to be equal to 9, and divided by tau p. Okay, and then we have our kp is 1.5, and then our delta u is equal to 100. Okay, so that's going to be equal to 60 divided by 150, 1 minus e to the minus 9 over tau p. We want to solve for tau p. And so let's see, that's going to be equal to, let's see, 1 minus 6 over 15 equals e to the minus 9 over tau p. Okay, and then we'll take this and just do a little bit of algebra here. Take the natural log of both sides. So the natural log of 1 minus 6 over 15 equals negative 9 over tau p. And so tau p is going to be equal to negative 9 over natural log of 1 minus 6 over 15. Okay, so we were able to get our time constant. Let me just see if OneNote will do this for me. Negative 9 divided by natural log of 1 divided by 6 divided by 15. Okay, and I think I might need an equal sign on the other side. Let me see if it'll do this for me. There it is. So we've got a time constant of 17.62. So that's how long it would take to get 63% of the way to 150 miles per hour. Okay, so that was just a problem that we came up with that demonstrates the use of those equations. Again, just to review, we started off doing some just some control system terminology in terms of the actuator, sensor, and controller, identifying those for a control system. For feedback control, we did an empirical model identification with 1 input and 2 outputs, and we identified the kp, theta p, and tau p for each of those. And then we also developed a model from first principles. This was from a species and an energy balance. We found the steady state values. We linearized those to come up with our final linear model. And the final thing we did was use some of these equations for the first order linear system and formulate a problem that helped us characterize the automobile performance based on something they might give you from an auto dealer. Okay, again, come back to this review, And I'd say go through, this exam, but there's a lot of other material there, a lot of videos, example problems that you can review as you prepare for this exam, and good luck.